Hey folks, back here again, where we're going to kind of just pick up where we left off last time in our videos here, where we're taking a look at evaluating limits. And last time we talked about evaluating limits and the concept of continuity, where if our function is continuous at the value of x equal to a, the value we're approaching in our limit, we can use what's known as the substitution method to evaluate that limit and be pretty confident in our result, right? Due to that continuity. Continuity implies that the two-sided limit exists at that point and is the output of the function. It is the dependent value at that particular independent location. All right. We established that in the last set of notes. We want to go a little further in this set of notes and start to look at limits at discontinuities, right? How do we consider finding the value of a limit where the function does not exist at that value, where there is a unique behavior in the graph where when we sketch the graph, we have to pick up our pencil, right, at that location. We have this discontinuity, this hole or this gap in our graph. And what we want to talk about is the different types of limits that we can encounter when that is the case, and really what are some, again, strategy for evaluation. And we're going to find strategy is not going to change up that much, folks. So let me get into it here. Let me bring over the notes. Bring these up. Here's the notes, folks. All right. We're going to look at what are called limits at discontinuities and the case for infinite limits. All right. And we will define all of that in this set of notes. All right. Set myself up here. All right. Okay. Again, where we pick up from last time, right, is this idea that we refer to as substitution method. All right. When a function f, when we consider a limit as x approaches a for a function f, right? If f is continuous at x equal to a, then what we know right away is that the limit of f at a is equal to f at a, right? We know that the limit for our function as x approaches a is going to be equal to the dependent value of our function when the independent value is a. Right? And we can use just a method called substitution method, which more or less implies that you're taking this value of x equal to a and you are substituting it in, right, to become the independent value within your function. It gets the name substitution method. That's the common name that we often call this process, and this support for the result, right? Right. How did we find our result in this limit? We found it through substitution method, right? Which more or less relies a lot on continuity, right? However, if f is not continuous at x equal to a, substitution method becomes unreliable in explicitly yielding the value of our limit, right? We can't be so quick to say that we found the value of our limit using substitution method. The analysis requires us to go a little further when f is not continuous at the value of x equal to a. All right. Here's what we end up saying. When f is not continuous at x equal to a, there are several different results that we could encounter, right? We are going to see several different possibilities. And we can't be so quick to judge. All right. Well, to begin with, when f is not continuous at x equal to a, there is the possibility that a limit still exists and we can evaluate our limit. or there's a possibility that our limit simply does not exist, and we can't evaluate our limit, right? And then there's also a third possibility that the limit, if it can be evaluated, it could be the case for an infinite limit. All right? So we have these different cases that can all be encountered, or can be be possibilities, right, when we consider evaluating the value of a limit. All right. So what we often do to further our functional analysis beyond substitution method is that we consider the values for the left and the right hand side limits. We always want to, when substitution method can't be considered reliable because we have a discontinuity at x equal to a, we do have to take our analysis a little further and consider what are going to be the left and the right hand side approaches. Right? If we remember in theory, the left and the right hand side approaches are always going to exist. Right? Well, I should say they're always going to be able to be evaluated. Right? They can always be evaluated. These limits can always be evaluated. And if it can be determined that the two limits are equal to each other and equal to the value at L, right, at the same time, we can conclude that the limit for the two-sided approach is also equal to the value of L. Right? We always continue our analysis, right, beyond substitution by looking at what would be the two-sided, or the corresponding one-sided. Okay, here's where I'm getting mixed. We look at the two different cases, right, for each of the individual one-sided limits that correspond to our case for the two-sided limit. Right? And we evaluate each of those individually. One-sided limits can always be evaluated. I changed this up just a little bit here because I didn't like saying could be existed. We really have to be careful with that term existed. We're going to be introduced to, in this section, the idea of infinite limits. And some textbooks, more than others, place an emphasis on the idea that an infinite limit, although is the result of a limit calculation where we have a potential, well, where we do have a discontinuity in that function at that value of a, we can't have a value, right, that's going to be what we call an infinite limit. The limit itself doesn't truly exist as a real number value. So some books, some authors, some argument is made where we say that an infinite limit does not exist. But we don't throw does not exist out as the solution to an infinite limit. The solution to an infinite limit is going to be exactly that. It's going to be a value involving infinity. All right? But infinity is not necessarily a location that we can say exists along a number line. Not like what we've seen for the cases that have not been infinite limits, right? Every other limit that has existed at a particular location along a number line, right? Which, when we use that term exist, is really what we're also trying to say. We have to be careful using that term, all right? So I'll say these limits can always be evaluated. Right? That's why I changed it up a little bit there, because I want to watch using that term existed. Right? Especially when discussing infinite limits. Right? One-sided limits can always be evaluated. They sometimes evaluate to a real number along a number line. Sometimes they might evaluate, as we're going to see, to the case for an infinite limit. Infinite limits, however, aren't always, well, we have to sometimes keep in mind that they don't necessarily exist like a real number does. All right? I do give an example here, right? I go back and I just recall, I think one of the last examples we looked at in our notes for continuity, and we had studied this piecewise function seen here, right? Where in this piecewise function, substitution, when we were asked to find the limit as x approaches -3 for function f of x, substitution does produce a result. When we substitute -3 into this function here for x, it substitutes itself into the second part because that's where x is greater than or equal to -3, right? Which means it substitutes itself into this value of x seen here and yields the value of 12. But as we had seen, this limit did not exist, because at -3 there was a discontinuity, right? At this boundary in -3 that separates the two pieces, there was a discontinuity, and that result from substitution becomes unreliable, right? That result of 12 is not the answer here. What we had to do to draw our conclusion in the end was keep in mind, look at the behavior from both the left and the right-hand side. And what we saw for the behavior from the left-hand side, I believe, was that we actually approached the value of -4, right? If we plug in -3 here, we calculate the value in -4, right? I had that calculation wrong in my last lecture, and we corrected that at the end. But yes, it's -4. And as we approach -3 from the right, however, the value seen on the second piece, again, as we had noted, we see that we're actually approaching the value of 12. So the left and the right-hand side approach give different results. So the two-sided limit did not exist. And I bring this example back into play just to begin to emphasize that when we have a discontinuity at our value of x equal to a, right? The result from substitution method, the result of just plugging x equal to a into our function for the value of x, which means we would be substituting it into this second piece here, does not yield reliably the value for the limit. Because the value for the limit in this case does not exist, right? It was not the value of 12, right? And that unreliable result was due to the fact that we had this discontinuity at this value of x equal to -3. Why a discontinuity there was because the left and the right-hand approaches were did not yield the same value when they were evaluated, right? We failed continuity there because we failed criterion 1 in our test for continuity, right? So I bring that first example up simply for that reason. I want to show you that you can't always trust substitution, right? When there's a discontinuity at your value of x equal to a. I do look at another example here. Let me not destroy my problem. Let me bring it into focus. Here's another example. Excuse me. Where I also want to try to illustrate. And I think, well, let's jump into this and I'll comment. Consider this limit. The limit as x approaches 2 for function f of x. For this piecewise function. All right, let me move that arrow so you can see that. The first piece in this function is linear, and that's linear whenever our x value is not equal to 2. And the second piece in this function is also linear, but it's uniquely in its linear behavior what we call a constant function. The second piece is constantly the value 1, but that's not a lot of places. That's only when x is equal to 2. But what we uniquely note at x equal to 2, that is the value, the boundary that boundary value is the value we're approaching within our limit. All right? Now, if we try substitution method here, right? If we just substitute 2 into the function for x, the conditions set on this piecewise function say, well, when x is 2, you're going to have to be the output of 1. But we want to be really cautious there, because I don't believe 1 is the result we get when we consider approaching from the left and the right. When we consider approaching 2 from the left and the right, well, that's when x is not going to be the value of 2, and is going to put us approaching on this piece we call 5 minus x, on that linear piece, right? 5 minus x. And how do linear functions behave, right, for limits along them? Well, they're continuous over their entire domain when not in a piecewise nature. So the value of this linear function alone, when x approaches 2, is going to yield the value of 3, right? We can see through substitution into this first piece just to consider the behavior of the limit as we approach along this first piece, right? Substitution method is going to produce the value of 3. And we would get 3 from both the left and the right-hand approach, because we would expect that with the continuity of the linear function 5 minus x at the value of x equal to 2, when we are able to have that continuity in our function. Right? What we see here, right, is that yes, this limit does exist. It's a little different than the previous example. It's another reason I'm showing you this. This limit does exist, but it's not the result of substitution method. Right? This limit exists, right, as we had noted, at the value of 3. Right? The limit from the left-hand side for our function and the limit from the right-hand side for our function illustrate linear behavior, right? They illustrate behavior, right, along this linear function for the case of 5 minus x, right? What we might say is both of these are equal to the limit as x approaches 2 for the argument of 5 minus x would be equal to the value of 3. Right? Indicating here, and again, the sense that the value of the limit as x approaches 2, the argument we were interested in, is equal to the value of 3. Right? Since the left and the right-hand approach is equal to 3. Now, do I say that in this? I got to be careful. Yeah. All right, I do make final comment on that down below here. I just wanted to make sure I said that. But again, notice f of 2 is the value of 1. Right? It's going to give us the value we see here in the second piece, this value of 1. Right? F at 2 is equal to 1. That's what substitution would yield. Well, the substitution here is unreliable due to the fact that we have a discontinuity at the value of x equal to 2. All right? The discontinuity in this case is actually due to the fact that we failed the test for continuity, right, in the third criterion. Right? The limit of this function as x approaches 2 does exist. It does exist and is equal to the value of 3. Right? That's the first criterion. The second criterion says that our function f has to be defined at 2. And it is. It's defined to be the value of 1. What criterion 3 says about continuity is that those two results have to be equal to each other. and they're not in this case. So that's why function f here has a discontinuity at x equal to 2. And when we see discontinuities, right, at the value that we're approaching within our limit, we cannot trust substitution method alone, right? We have to go a little further in our analysis, right? I'll tell you, substitution by itself is always going to be the first approach. Whenever I begin to evaluate a limit, and particularly not for the case of a piecewise. When piecewise functions are really a unique case. This piecing together different dependent values over different intervals within the domain are functional behaviors, but they are kind of unique cases where substitution gives these variety of possibilities that we see above. If we think about non-piecewise scenarios, typically how I approach those without having to spend too much time with continuity to begin with is I just jump into substitution method and see what happens. Right? Substitution method can, when you're dealing with a non-piecewise function, when you're dealing with just a function that has one dependent behavior over the entire domain of the function, right? You can encounter the case for your limit existing at a real number along the dependent axis, along the vertical axis, or you can encounter in the substitution result what would be an undefined result, right? Or you could encounter what we're going to see just a little later on in the notes, in some coming videos, is a result known as an indeterminate form. Substitution, when working with non-piecewise functions, can produce real numbers, it can produce undefined results, or it can produce what we're going to find are what we call indeterminate forms. And the idea of an indeterminate form might be nudea. And whereas undefined results, we've given the answer that of undefined before in our past, where we haven't necessarily done that with indeterminate. So we're going to spend a little bit of time with indeterminate forms. All right? All of this, right? Substitution method, although at times can be unreliable, typically always gives us useful information about the value of the limit. If not the exact, at least the information is still going to be useful in terms of how do we progress further into the calculation of the value. All right. In the last case, that limit's value was equal to 3, and that's what the notes finally say here. So I'll let you just read through that. But let's get into what we're looking at here. Note, well, for this case, I actually illustrate this. I think I want to say this. This is what I wanted to comment on. We had our test for continuity. And if we look through some of the last few examples of piecewise functions, those last few examples of piecewise functions have illustrated the different scenarios for how our test for continuity can fail. Right? As we had said, our test for continuity can fail when the left and the right-hand side approach don't give the exact same result. Right? That was this first result up here, right? This first example. This example that was in our last set of notes. right? Our test for continuity can fail because the left and the right-hand side values don't give the same result. It can also fail by simply our function not being defined at our value of x equal to a. That's another result that can occur. Or it can fail because not because of criterion 1 or criterion 2. It can fail due to criterion 3. And this third case is illustrating that case for criterion 3. Again, we note the function is defined at 2 here. It's this solid dot. The limit does exist as we approach 2, because as we approach 2 from the left or the right, we see that we approach the same value, this value at 3. Right? Where this fails for continuity, we can see it's not continuous because we have to pick up our pencil. Right? We have this hollow dot in our graph. We have, in a sense, this gap form. Right? Where it fails is criterion 3. This limit of 3, right, for the left and the right approach that we see along this line is not the dependent value of the function f when we are at the independent value of 2, is not this value of 1, the value of f where we are defined at the value of 1. It fails that third criterion. So I wanted to show you that with this example also. Right? I think I had mentioned that in the last notes. I didn't have that example on hand at the moment, and I thought that it had been somewhere in our notes. It was actually right here in this note to come. All right? So just take note of that there. You're right, folks. I just took a break. Yeah, these get long. I realized that we were at about 26 minutes there. So, no, I wanted to take a quick little break there. I try to make short videos, I swear. This set of notes is not that long with illustration and some work involved, right, with some mathematical equations laid out vertically. So, it doesn't take up much space, but for some reason, my videos just get long, and I don't know. It's just, I guess, the way it's going to be. I am trying to talk, well, like I said, give you an honest lecture here, right? An authentic lecture. At the same time, present you with some notes that certainly we wouldn't want to do by hand if we don't have to in this format. So, yeah, but again, occasionally I'm going to dip off into the background there. And usually that means I just pause the recording for a quick moment and I am back. And maybe at that time, you yourself take a break if you need to. And if these ever do get long and all you're doing is reviewing, I believe you can, watch me in double speed, and you'll get through this material in half the time if you do that, right? And just right underneath the settings, the little gear marker, I think right below me here. You'll find the gear marker in the settings menu, and you look under speed. I think you can adjust the speed of YouTube videos to play at 2x speed or 1.5 speed. So you can always watch me in that speed. And if you are doing that right now, I probably sound pretty different, right? But that's sometimes fun to watch. So if you're looking for just a little more energy in the video, that's where you might get it from. My apologies. Oh my goodness. Don't make me sneeze again. All right, we're good. Let's see here. Let's pick back up. Let me go from here. When we have discontinuities at the value we're approaching in our limit, substitution method becomes unreliable. However, it doesn't necessarily give us useless information. The information from substitution method will always have a little usefulness to it. It's part of the equational analysis that's involved with analyzing the value of a function, or of a limit, right? It's all part of that functional analysis, but specific to the case of evaluating a limit, right? It's part of that limit analysis. There's always some useful information from substitution. Right? Yeah, let me scroll down here, bring some notes in effect. Because there are times where, for instance, you apply substitution method, and what you end up with is not a real number, but you obtain an undefined result. And what's an undefined result? Well, that's when you have any real number divided by 0. And I should be careful there. Any real number where that real number is not itself also 0. Right? You mostly encounter undefined results in the case for non-piecewise functions, right? When we're not looking at a piecewise function, in the case for a rational function. You have to be cautious as you perform substitution. When you perform it, you're going to substitute it into your numerator, the value of a, and you're going to substitute into your denominator the value of a, the value you're approaching in the limit, and sometimes it gives you a real number, which is great. That's if you're continuous at that value. But sometimes it gives you an undefined result, which means the top is a real number that cannot be the value of 0. The numerator is some real number that can't be the value of 0. And the bottom, the denominator, is the value of 0. Right? Remember in math, if you divide by 0, take any number other than 0, and do 0, this doesn't work with. But if you take any number other than 0 and divide by 0, that is undefined, right, in its result. You go, well, what about 0 over 0? And I go, well, if you're performing substitution method and you obtain 0 over 0, that is actually going to be a case for what we call an indeterminate form. Like I said, that's a video or two away. We're going to discuss indeterminate forms. All right. I know right now you're going to get 0 over 0 in some of your work, and you're going to want to say that's undefined, and you're going to encounter some incorrect answers then, right? The only time you have an undefined result is when you have a real number in the numerator that is not 0, and you have 0 in the denominator, right? When you have this form very specifically stated in this manner, right, with these conditions. This is when an undefined result happens. Otherwise, if this result is not true, p equals 0, right, you have what's going to be found to be called an indeterminate form, which is exactly what the name implies. You cannot determine, right, the value of 0 over 0 from the form 0 over 0. It's an indeterminate form. We'll talk more about that in future videos. But what we're talking about is having a real number that's not 0 divided by 0. When you perform substitution in that method, in that manner, and you get that case, you could have the case for what's known as an infinite limit, right? Or this is the option that's possible, along with, you could also have the case for the limit simply does not exist, right? The value of the limit might not exist, or the case of an infinite limit could also be encountered. Let's take note, right? You could have those situations arise. Here's an example of an infinite limit. Right, here's this example. Image is kind of big, so it jumps right down there. But let's take a look at it collectively. All right. We might consider the limit as x approaches 0 for 1 over x squared. Right. For 1 over x squared. Right. Now that's going to be our function of f. Right. And what we should note right away is there certainly is a discontinuity at x equal to 0. Right. Our function f does not pass what criterion on our test for continuity, right? There's a discontinuity there. What criterion does it fail? Well, right here, if you substitute in 0, if you perform some substitution method, you're going to run into 1 over 0 squared, And that is an undefined result. All right? It fails criterion 2 in our test for continuity. All right? What you'll notice in the form, and I went ahead and added this, all right? 1 over 0 squared is equal to 1 over 0. We obtain through the substitution this format. Let me highlight just it strictly. We obtain this format P over 0, where certainly 0 is in that denominator. And in the numerator, we have a real number, 1. 1's a real number that is not 0. That 1 is certainly not 0. And what this produces is an undefined result. And what we see happen in the graph is what we refer to as an infinite limit. All right? If you keep in mind, the graph of our function 1 over x squared is actually going to have a vertical asymptote where the denominator equals 0. Right? If we take the denominator x squared and we set it equal to 0, we're going to find that that's going to be at the location of x equal to 0. And you'll notice in this graph right here at that location, right, there is a vertical asymptote in our graph. And if you remember back to college algebra, where all of this knowledge is coming from, as we approach that vertical asymptote, there's one of two behaviors we can illustrate. We can either go up it towards positive infinity, but never cross or touch it, or we could move down it towards negative infinity, getting closer and closer and closer to it, but never crossing or touching it. In a sense, we think of it, the graph would either, its outputs would become bigger and bigger and bigger and head towards positive infinity, or they could get smaller and smaller and smaller and head towards negative infinity in value. And what we see for the value of 1 over x squared is that as we approach 0 from both the left and the right-hand side, the output behavior grows without bound, right? Those values just get larger and larger and larger. This is a case where we have what's called an infinite limit, right? And in fact, if we evaluate this limit, right, we would say the value of this limit is equal to positive infinity, right? As for the limit of this, right, what we notice is as x approaches 0 from both sides, right, our function 1 over x squared increases without bounds towards infinity. Right? You think about taking the reciprocal of very small numbers that are really close to 0, you're going to get very large numbers. Numbers that are really close to infinity. Like the reciprocal of 1/1,000,000th, 1 over 1,000,000,000, well, that's reciprocal is 1,000,000,000. It's a very large value, right? So since f of x is going to head to infinity as x heads to 0, we can conclude that this limit must be equal to infinity, which is this result that's actually known as an infinite limit. Right? We have to be careful saying that it exists at infinity, because that kind of implies you can get to infinity. But what we say is the limit is equal to infinity. And what that really specifically means is that your output of the function, this dependent value, is that it approaches infinity. Infinity, however, is always going to be slightly out of reach, right? So your approach is going to be occurring forever, right, in our calculation. And that is exactly what we see here happening in this vertical asymptote, right? Both sides of this graph are going to go up forever, right? Trying to reach positive infinity. They're going to be getting closer and closer and closer to 0 as they do, as implied by the shape of this graph. They're never going to bend back away from 0. If they bent back away from 0, we couldn't call them functional behavior. And 1 over x squared is illustrating functional behavior. Right? So they're always going to be getting infinitesimally close to 0 while trying to reach that unreachable value of infinity. Right? This all occurring, again, as x heads off to the value of 0. Right? That's what's known as an infinite limit, right? And I think we put that in a definition here. Yeah. I set that up here as a definition. Let me bring that out of focus for just a moment, right? And relate this to the above. Oh, quit jumping. It's that image is large and it wants to show you the whole thing as soon as it comes into view. Let's see here. By definition, right, this is known as an infinite limit because for the function f of x, right, f of x approaches positive infinity. It can be one or the other. When we say plus or minus infinity, that or is exclusive, right? It's positive infinity or it's negative infinity. This is plus or minus infinity is how we read that. So that or is exclusive. It's exclusively positive infinity or negative infinity. We don't mean both. All right. In terms of f of x behavior. All right. If the output of the function approaches plus or minus infinity as x approaches the value of a, then what we say is that limit as x approaches a for f of x is equal to that value of positive infinity or negative infinity, right? Which is known as an infinite limit. This considers the case of both f approaching strictly positive infinity, exclusively positive infinity, or exclusively negative infinity in this result. Right? It's not going to approach both It's not going to approach both from the left or the right at the same time. Right? It's not going to go approach from the right and go both up and down to plus or minus infinity. It's either going to go up to positive infinity or go down to negative infinity. Otherwise, it wouldn't be functional, right? It wouldn't be a functional behavior. We wouldn't be discussing that behavior in this example. This is for a function, right? And from the left and right, you don't have an infinite limit if they go opposite directions. If this one's going up towards positive infinity and this one's going down towards negative infinity, you don't have an infinite limit because the left and the right hand side approach aren't yielding the exact same value, right? Of positive infinity strictly or negative infinity strictly, right? Exclusively, right? The previous graph, we were able to say it was positive infinity because the approach from the left and the right both approach that value of positive infinity. But if the left-hand side was to go and approach and head down the vertical asymptote, we would say that limit here does not exist. Both the left and the right-hand approaches, however, would be infinite limits by themselves, right? Note, we probably should add that here. Note, this includes the cases for the one-sided limits. Where x approaches a from the left-hand side and x approaches a from the right-hand side. I think we can say it that way. We could have a one-sided limit and have it head to positive infinity. And we could have the same for the, for one-sided limit, a left and a right, alone. For example, this left-sided limit alone is positive infinity. This right-sided limit alone is positive infinity. And just like with non-infinite limits that exist at a real number a, they always can be evaluated for the one-side approaches. You're not going to be giving answers that do not exist. You're not going to be able to you will not have the case where you cannot evaluate and are forced to say does not exist. All right. I want to make sure I say that as clear as I can. Again, because infinite limits are said often referred to as not existing, but it's just because of their infinity. All right. And I do say that here. Note, an infinite limit does not exist as a real number L, right, when we see this statement. All right. And instead, it really describes the behavior of f of x increasing or decreasing without bounds towards plus or minus infinity. Back to that idea of it's describing a change that's happening without boundary, for that change that's allowed to grow or decrease forever. Right? An infinite limit describes L as approaching positive infinity or approaching negative infinity in its value. Right? And actually in calculus, it can be used to further define what is a vertical asymptote. From algebra, we said it's where the output heads up or down towards plus or minus infinity. Well, that is it, but we can say that now with limits. Right? We can say a vertical asymptote exists in the graph of y equals f of x at x equal to a when the limit as x approaches a for function f of x is the case for an infinite limit. Right? When this limit is the case for an infinite limit, we can say that we have a vertical asymptote at this value of x equal to a. And this is also true and includes the cases for the one-sided approaches. This gives us a new way to define vertical asymptotes. All right. Let's look at some example. Well, first thing I note here is infinite limits can be identified by the discontinuity at x equal to a in our statement. Right? Where an asymptote occurs in the behavior of our function f. All right? Absent the graph of f, this asymptotic behavior, right, is what you identify through substitution method. Right? This method produces I just noticed this, produces the result p over 0, right? Where again, p is this real number such that p cannot be the value of 0. That's when you know you have asymptotic behavior at a real number of a. When you substitute it in using substitution method when evaluating your limit, and you encounter a result in this form under these conditions. Let's look at an example. I also go on to note then, when it is this case, when you do encounter this case of asymptotic behavior for your discontinuity, you want to consider then finding the corresponding one-sided limits. What you want to check on is, does criterion 1 in the test for continuity still exist or still check? Right? Is your discontinuity because of criterion 2 or only criterion 2? Right? Or could it also be, because your limit does not exist? All right? So you want to check that with your left and your right-sided limits. When you are evaluating a limit, you're typically going to start by just trying substitution, right? And when it's non-piecewise, That substitution is going to give you a real number, and that real number is going to be your answer. When non-piecewise, and it gives you an undefined result of p over 0, right, where p is not 0, then you want to go a little further and say, okay, I want to look at the left and the right-hand side approaches, because what I could have occurring here is an infinite limit. So that's what I'm telling you here in this note. And what you're going to be able to do by looking at your left and your right-hand side approaches is you're going to be able to evaluate the limit without having to get into the graph and be able to perform strictly a numerical analysis, which is really what you perform anyway when you're structuring the graph. In the case of a rational function, you're just going to be able to step out of actually having to go through the graphical process. Right? We might consider this limit here. Let me just bring this example into view. Right? If we look at this limit here, we might consider the limit as x approaches 4 for 2x minus 3 over the quantity x minus 4 times x plus a. Right? That is quite obviously a rational function, and we have seen these function types back in college algebra. And I helped you out a little bit. I wrote it in a factored form. Factored forms are kind of nice because they can be evaluated pretty quickly. Right? So kind of a hint there when working with rational functions in limits, cases where you might encounter infinite limits, getting to a factored form is often going to be pretty useful. Because what we notice here is we can evaluate this using substitution method pretty quickly for the value of 4. If I substitute 4 into the numerator, I'm going to have 2 times 4 minus 3. Well, that's going to be 8 minus 3. That's going to yield 5. That's not 0. But right away in the denominator, I can see when I substitute 4 into this first factor, the first factor's value is going to become 0. And right away, it doesn't matter what 4 gives us here. It's 12, but it doesn't matter because 0 times that 12 is going to be 0 in value. This can be any other number, and when you multiply it by 0, it's going to be 0. So right away, we know this denominator is going to produce 0 because x minus 4 is a factor in the denominator. And we're substituting in the value of 4. So this produces, through substitution method, an undefined result. I say that here, right? Notice substitution method produces this undefined result 5 over 0. It fits that form we've said as p over 0. So right away that tells us in our graph we have a vertical asymptote at x equal to 4. And what we want to now explore is what is the right and the left-hand side approach is going to give us. And you might say to yourself, well, how are we going to do that, right, without the graph of the function? And I'm going to say, well, we're going to do it through a bit of numerical analysis, right, where we're going to analyze the signs of the function. Because what we know about the left-hand, right-hand side approaches is that we're going to be able to say that they're one of two results. They're either plus infinity or they're minus infinity, because being one-sided, they must be able to be evaluated, right? As one or the other. We're not going to be allowed to say they do not exist. The limit where we can say it does not exist could be this limit right here. The two-sided approach could have the result of not existing. But as we approach from the left or the right, we're going to see one of these results or the other. Right? We know that because of this undefined result from substitution. Like I said, substitution method may not always give you a real number, but sometimes it's going to give you useful information. It's still going to give you useful information. Here it's going to tell us you could expect either the answer is positive infinity, negative infinity, or does not exist. Right? And where you have to step now further, to go further in the analysis to evaluate the limit, is to look at those left and right hand sides. And the way that happens is by considering the sign of the function. All right. So that's what I start to get into here. I say, so consider the left-hand side limit for this here. It must exist. And it must be either positive or negative infinity in value. All right. And to determine what it is, right, I'm going to simply evaluate my function near x equal to 4, where x is going to be just a little smaller than 4. I'm going to perform a numerical analysis where I'm going to use numbers that are near 4 but smaller than 4, like they're going to be like 3.9 and 3.99 and 3.999 or 3.99999, right? Just like I would with a table. But I'm not going to look at the specific value. What I'm going to pay attention to is what sign does this value have? The sign is going to tell me whether or not I have the case where I'm heading towards positive infinity or the case where I have the behavior of the function heading towards negative infinity, because the signs are going to be the same, right? If the sign is positive, I know I'm heading towards positive infinity. And if the sign happens to be negative, I know it's going to be heading towards negative infinity, regardless of the number that I happen to pick that's near 4 where x is less than 4, right? I'm going to be able to deduce what sign I'm going to have on my infinity in this result. All right. Notice for x near 4, where x is less than 4, here's going to be the sign analysis. Right, I have this sign analysis right here, and it's a little hard to see part of those, so I'll unhighlight, but where you don't see pluses, you'll see minuses in the value of f. And all I'm doing is I'm looking back at my function. I could look at it here or here, right? I'm looking back at this function, and I'm looking at the numerator and saying, okay, what do I get if I plug in a number that's just a little smaller than 4, like 3.9 or 3.99 or 3.9999? Well, I'm going to be, first of all, in terms of sign, I'm going to be plugging in a positive number, right? I'm going to be plugging in a positive number here if I'm really close to 4 and I'm smaller than 4, right? So 2 times that positive number is also going to be positive to begin with. Now, when I come along and I subtract 3 from it, though, I want to be careful, because if that number is smaller than 3 and I take 3 away, that whole numerator could become negative. But because I'm really close to the number of 4, I'm near 4, right? And I know if I was at 4, if I was actually equal to 4, I would certainly be larger than a number of 3. And in fact, what I need to be bigger than is 3, and the only way that 2x could be bigger than 3 is when x is bigger than 1.5 in value. If x was bigger than 1.5 in value, then 2 times x will be bigger than 3. Right? Well, if I'm near x equal to 4, I'm certainly going to be bigger than 1.5 in value. So right away, I know that 2 times this number is always going to be bigger than 3, and I know that numerator is always going to be a positive number in its result. Now, we perform a similar analysis on the denominator. I look at my first factor, and this is why the factored form is nice. Because I know how each of these linear factors is going to behave when I'm near 4 and a little smaller than 4. If I'm a little smaller than 4 and I take 4 away, as I do in this first factor, guess what? If I'm like 3.9 or 3.99 or 3.9999, if I'm just a little smaller than 4 and I take away 4, I'm going to be negative in my result. I'm going to be negative 0.1 or negative 0.01 or negative 0.0001, right? I'm going to be a negative number. So this first factor is going to be negative. The second factor, right? If I'm a little smaller than 4 and I add it 8, well, because 8 is, we're adding a positive value to another positive number, right? Because we're going to be just near 4, but a little smaller than it, right? We're also always going to be positive in value. So in that denominator, under these conditions, that first factor is always going to give you a negative result, and the second factor is always going to give you a positive result. And if those two factors are always going to be being multiplied in our denominator, as they imply by this functional form, they're always going to yield a negative. And if we take a positive divided by a negative, the result is always going to be also a negative. And a negative value, regardless of the number we pick that's near 4 when x is less than 4, right, will always be the value for our function, right? When x is near 4 with x less than 4, f of x will always be a negative value, right? So that limit for the approach along the left-hand side, right, will be negative, which implies we must be heading towards negative infinity for the result of it having to be an infinite limit, right? It has to be one or the other here. And because we know the signs will always be negative, we know that it must be heading towards negative infinity. There's no chance it can be heading towards the positive side. Now we can do a very similar analysis on the positive side. And very similarly, right, again, we'll see the numerator will always be positive. But it's where in the denominator, what you'll see happen is if we pick a number bigger than 4 and we take away 4 from it, it actually is always going to be positive. Where when we take that positive in the denominator and multiply it by another positive, you'll always end up with another positive result, where a positive divided by a positive is always going to yield a positive result, right? Implying that our function will actually always be greater than 0 when x is near 4 with an x bigger than 4. Our approach from the right-hand side should approach positive infinity. I have these backwards here. Let me fix this in the notes. I just realized this. Did I say that? This is the less than approach. Oh, no. Okay, we're fine. As for the right side approach, this is the left-hand approach. We were right there. We're looking at this approach now, and then I have the sign wrong here. That's what it is. It was probably a copy and paste error. That's what I'm missing. So that corrects it. F of x approaches positive infinity as x approaches 4 from the right-hand side. So that's one of the reasons I like to read through these with you here, folks. Put these videos together. It's kind of a way I can edit some of my work if I catch those mistakes. Right? So what must be true? Well, here we have the two we can see side by side. Well, kind of close. The approach from the left is negative infinity. The approach from the right is positive infinity. So what does that mean for the two-sided approach? The left-hand approach heads down to negative infinity. The right-hand approach heads up to positive infinity. So the two-sided approach, because we head to two different directions, right? We don't want to say values, we want to say directions. We say that limit does not exist, right? And that is what we see in our result here. Because the left and the right-hand side approaches aren't equal in their description of behavior for the output of this function, right? We can conclude that two-sided limit is a case that does not exist, right? It also doesn't exist because the one-sided limits also don't exist because they're heading up non-existent values in a sense, but it's not for the same reason this limit does not exist. There's some distinction there. This result also does not exist, but that's because infinity just does not exist. It's a direction, not a location. There's a little difference there, so we really want to make sure we understand that when we use this we throw out the term does not exist. All right. You will see an author say, yeah, plus infinity does not exist. But you don't want to confuse it with it's a result that you can state does not exist with. Because does not exist only considers an option when you're looking at a two-sided limit and the left and the right-hand side approach, or it's on your screen backwards. The left and the right-hand side approach don't approach the exact same value. All right. Let me take a quick break here. Sorry, folks. We're at hour 5 on that. I just wanted to take another quick break. It had been almost 40 minutes since the last break. Well, I know it's getting long. I wanted to look ahead and make sure that when I come back here and tell you, yeah, we're almost done, right? I promise we are almost done. I got one more example for you. I got a conclusion I want to make here and get into that example. And I apologize. I always think about making short videos, but it doesn't always happen that way. I always like to joke. I was classically trained as a teacher, as an educator. I've been through the whole education process in terms of going through and doing my observations. I did student teaching. I took all the education courses, what they call the pedagogy courses for teaching mathematics, the high school and the middle school level. And I had a professor back when I was taking these classes tell us that teaching is a lot of repeating yourself, right? It is a lot of saying the same thing over and over and over again. And the one mistake you don't want to make is to say the same thing over and over and over again the exact same way, right? Because all that catches is, the portion of students that understand that exact same way. So some of my lectures, I'm often saying the exact same thing multiple times, folks, and it's my apologies. It's, I could just say this once, which, if you thought about that, would be I could just read this to you. And at which point that would just be story time in mathematics at a high level. And that's not what I want to give you. I'm trying to give you a bit of an authentic experience. So you'll hear me, repeat things several times here, and that's why. And then even in classes, it's a lot different because not only am I, presenting the material as I do, but I'm also trying to engage you along the way, presenting questions and giving you time to respond and directing you in different ways to think. So yeah, that's, just, I'm sorry, some of the authentic me. So this is long. Shut up now and let's finish, right? Where am I at? Cursor. Let's get down here. Bring this into view. I do have a conclusion, right? In conclusion for this limit, right? When a discontinuity exists at x equal to 5, all right, there are always going to be several results possible, right? To explore these possibilities, what you want to seek out a substitution method, all right? You always want to start with substitution method, I should say, all right? And then from substitution method, you're going to follow with some analysis of the one-sided limits, all right? An analysis of these limits is always going to be the next step in the process. When a discontinuity exists in this limit at the value of x equal to a, right? We saw it in the piecewise case and we see it in these non-piecewise cases, all right? You're going to want to pay attention to continuity. Piecewise cases present cases where you have discontinuities, and then oftentimes rational functions will produce those cases, as well as even radicals, logarithmic, trigonometric functions, right? there are instances where we want to be cautious, right? And our analysis, once we try substitution, is when we get that that form P over 0 where P is not 0, right? We can go down the road of infinite limits, which involves analyzing left and right-hand side approaches, right? Just like you would in a piecewise defined case, right? Where you were looking at a limit where you had a boundary of potential discontinuity. You would just look at the left and the right-hand side limit, right? So, I always say you can try substitution, watch it in the case of piecewise for discontinuity, but in the non-piecewise case, if you encounter an undefined result, in either of those situations, you're going to want to seek out two-sided limits, right? Piecewise or not. All right. Here's one more example. Consider this through a slightly different rational expression. Here I incorporated the natural power function, right? E to the x. Here I have e to the x over x minus 1 quantity squared, and I'm interested in the limit as x approaches 1. And as I've hinted to, how you approach limits, particularly non-piecewise limits, first step is just substitute. Substitute in the value of 1 and see what results. And here you can see in the numerator, you're going to have e to the first power. E to the first power, right, up here in the numerator, well, that's just e. That is a real number, but it's not equal to 0, right? In the denominator, though, if you substitute in the value of 1 and you subtract 1, you end up with 0. And 0 squared is 0. The result of the denominator produces 0. And what you end up with is an e over 0, that form p over 0, and the result is undefined, right? So I think that's the next thing I say here is note from substitution, right? We encounter an undefined result. So what that tells us is there must exist a vertical asymptote in our graph at x equal to 1, even though we don't have the graph right there in front of us. And what we want to produce now is an analysis of the corresponding one-sided limits, an analysis that we can perform numerically and doesn't require us to sketch the graph of this function. All right? Now, if we perform a left-handed side analysis, right, we're going to want to think about what's the value of f, our function, for values of x near 1 when x is less than 1, like 0.9, 0.99, and so forth, right? If we plug in a number close to 1 into the power of e, you're going to have an e value raised to a positive power. You're going to have a positive value raised to a positive power, which in that numerator is always going to be positive in value. All right? In the denominator, if we plug in a number that's close to 1 but less than 1, the first thing that's going to happen to that number is we're going to take away the number 1. If we take a number 1 away from a number just smaller than 1, we're always going to end up with something in the negative region, something a little smaller than 0, a negative number. So to begin with, we'll have a negative inside this group. But that group, we can see here in the notation, is going to be squared, which means we're going to take a negative times a negative, which can be interpreted as being positive in value. In the end, we result in a positive over a positive value, which is also positive in value. Implying when we look at that one-sided limit, the limit as we approach from the left, with the vertical asymptote at x equal to 1, the choices we have are that it heads to positive or negative infinity, and with a sign analysis giving us positive, we know that we must be heading to positive infinity in value. And similarly, if we perform that analysis for the approach from the right-hand side, right? Again, in the numerator, we would have a positive raised to a positive power, which would be also just positive, right? If we use something near 1 but greater than 1. But in the negative, or in the denominator, right, we would have a number close to 1 but bigger than 1, where we would be subtracting 1 from that value, which yields a positive result, right? If you take 1.1 and you subtract 1, you're going to end up with positive 0.1 in value. You're going to get something just a little bigger than 0, right? Well, that positive value squared is that positive times a positive, which is also a positive. So a positive divided by a positive will yield, again, a positive result. Implying that if this one-sided limit has to be positive or negative infinity in value, this right-hand approach also yields the value of positive infinity. And because the left and the right-hand side approaches both give us this result of positive infinity, what we're able to conclude is that the corresponding two-sided limit must also be, must also be equal to positive infinity. Right? If that didn't get your attention, right? The left-hand approach and the right-hand approach, in this case, through a sign analysis, we can see both equal positive infinity. So we can conclude that the two-sided limit must also be equal to positive infinity. All right. My apologies on that sound. Every time you reach a boundary in my text editor here, it'll ding for us, and my volume is just turned up pretty loud. So, but that is what I have to say today, folks, in this set of notes. I'm going to end it there pretty quickly. I've already said a lot of additional here. And I will see you in class, where we will also have a little discussion on these ideas. And just to give you some heads up, we're going to continue. We're going to look at next a little different case for infinity, where we're going to look at limits at infinity. We just talked about infinite limits. There is a difference, all right? And we'll discuss that in the next video. So thanks for watching, folks, and I will see you in the next one.